Hello, my name is Andrew Monchi. Today, for my midterm 2, we'll be doing problem number 11, where in this problem, we are going to show that in 3 dimensions, rotational invariance of the Lagrangian implies the conservation of total angular momentum. So, to start off with, we're going to first assume that the Lagrangian of the n-particle system is unchanged by rotations about a certain symmetry axis. Now, for this problem, we're going to assume the symmetry axis, we're going to call it the z-axis. Doesn't really matter what we call it here. And so, for part A, we first want to prove this relationship right here at the bottom, which is that the change of the Lagrangian, which is that the sum of all the change in the Lagrangians for each of the individual particles, with respect to theta, is equal to 0. Or in other words, and to do this, first of all, we're going to suppose that each of the n particles is going to simultaneously be translated by an infinitesimally small amount epsilon in the theta coordinate. Theta, in this case, being the horizontal or azimuthal component of the rotational or in spherical coordinates. Essentially, here, think of it as when if you're rotating around this axis, the theta that's changing, that's just going to be the amount that's changing the actual rotational part of it. Okay, so to get started with, we first express the Lagrangian as so, with this, in this initial state, the Lagrangian equals this Ri, Bi, theta I. So let's count this as the initial state. And then we have the state after it's been translated, which is basically going to be the same, but with theta I plus the infinitesimally small amount epsilon. And so, because the problem said that there is rotational invariance, this implies that the amount that the Lagrangian before and the Lagrangian after the translation are going to be the equivalent. So upon establishing this, we can now take this one post-translation Lagrangian, and we can expand it through the use of a Taylor series taken about the point epsilon equals 0. When we do this, we get this little expansion right here. These components basically being, first we have our initial state of the Lagrangian, plus the sum of our Lagrangian, plus the sum of the derivatives of the Lagrangian, taken with respect to theta, times epsilon, plus this final term right here, which is just higher order epsilon terms. Now, with this final term right here, this term is actually irrelevant because epsilon is infinitesimally small, as stated before, and so these terms are going to basically be, we can basically approximate it to 0. So now we're left with this little equation here, but we've already established that the initial state of the Lagrangian and the state after it's been translated are the same, so we can just, so those two will actually cancel each other out. So basically we're left with that 0 is equal to the sum of the derivatives of the Lagrangian taken with respect to theta for each of the n particles here times epsilon. Epsilon being the same for each of the particles. But we will need this to be true for all values of epsilon. And so for this value to be true for all values of epsilon, that means that we basically just get this relationship right here. Yes, this relationship does, once again, just imply rotational invariance, which we've already assumed to do this derivation anyways. But what it also does is that it will help us in part B, where we're going to now show how this would imply that total angular momentum will be conserved. As first we start off with our standard Lagrangian for an individual point, and we're going to sum up all the Lagrangians as seen right here. When we take the sum of all the Lagrangians, we can first distribute this sigma term to both of our other terms right here. So first of all, this sigma term right here is dl d theta. That's just a term from part A. That's 0. And so now for the rest of these terms here, we see is ddt of the sigma dl by d theta dot. Now this is known to be actually equal to our angular momentum. I have a little proof right here about why that is angular momentum, but yeah, it's going to be a well-established fact that the dl by d theta dot is going to be angular momentum in this case, and that's angular momentum for a specific individual particle. And so then we have this ddt summing up all the angular momentums for the system here, or in other words, that's going to be the total angular momentum. So we say that the dl, the total angular momentum, by dt is equal to 0, or that the angular momentum, the total angular momentum, does not change in time. Now, in terms of what this actually means, it basically means that it is conserved, in other words. And this is really just another showcase of Noether's theorem. Noether's theorem basically showcasing how an invariance will imply a conservation law. And you can actually do an analysis similar to this one for any of the conservation laws. Energy, linear momentum, and you can do it in 2 dimensions as well as 3 dimensions. And I would implore you to do that. Well, thank you for listening, and have a great day.